Hello everyone. The class we're going to have today is the project of an autonomous robot. We'll be using the infrared sensor and an ultrasonic sensor for the in-depth discussion of a project that is more programming oriented. In the autonomous vehicle competitions that are usually found, these two basic sensors are mostly used. Of course, if you have more advanced requirements, there are others as well. Our class focuses more in the basics, so we will not be introducing all the parts. We will not introduce all the parts. For our production project, we will repeatedly be using the infrared tracing sensor in basic topic discussions, such as the tracing of black lines. After finishing the basic discussion, we expect students to think about different approaches when dealing with more complex and mixed topics. How should my sensor perform the detections, and how to observe each one of these approaches? What rules should be established, and how the assertion should be performed? What kind of adjustments should the vehicle make during motion? After you finish running your program, you realize the vehicle is not moving the way you expected and tends to work outside the black lines. You need to observe and understand why it is going outside the borders. What is the reason behind this? Whether my rules were set wrong, or the vehicle's power can keep up with the rules. You should be able to think the big picture, then make corrections. The other type of sensor is the ultrasonic sensor. For this part, we will be using examples of mazes. We need to consider that there are not that many connector pins in the vehicle's node MCU, so we will only use a single sensor, which can still work through a maze. During our class, we will tell you how to use a single sensor for ultrasonic measurements to work through a maze. In addition to these two basic topics, there will be some others with mixed applications. What are mixed applications? Some cases that are for tracing can also use ultrasonic measuring. In our following class, we will start with the basics. Then we will give you the chance to try an advanced part. Next, we'll begin with today's class. First, let's take a look at the infrared tracing sensor. For the infrared tracking sensor, we will cover the tracing part. In this unit, we will give the robot the following command. We want it to move along the black line. Our controller will drive the motor. The motor will be the output. The vehicle will move by means of the infrared sensor. The status of the black line on the floor, since it follows the black line, when it deviates from the black line or approaches one, it will send a feedback to the controller through the output connector pin based on this information received. The controller will figure out which direction should the vehicle go and perform detection in a looped manner, and adjust the power output of the motor so that the vehicle can move along the black line. This is a basic principle of the tracing sensor. Next, regarding how to extract the readings from the infrared sensor, or some basic if conditions. If you have forgotten a little bit, you can go back and rewatch the previous recordings to review a little. Let's take a look at our first exercise. You'll be given a vehicle. We're going to set up this vehicle to move forward and then stop if it encounters a black line. Okay, let's take a look at our figure. It looks like this. It's a vehicle. We'll give you an oval-shaped, colored black frame. When the vehicle moves forward and encounters the black line, it will stop. We will follow the flow chart on the right. First, we will use our smartphone to control its power. We must send out a command for the vehicle to move. It will slightly move forward. Next, we need to activate our sensor. After it's activated, we will use the infrared sensor to sense the floor status. In the beginning, it will be in a white area, so it will move forward. It will evaluate if it's encountered a black line. False means no, so the vehicle will move forward. After it moves forward and has finished with this step, it will go back. After moving forward, it will go back to the beginning of the flowchart and ask again about the black line status. If it is still in the white area, it will go through this loop until the vehicle encounters a black line. When this happens, the reading for our black line is true, so it will perform a stopping action. Let's take a look at the program code. Let me remind you that although you've already seen this and you've been taught this concept, you still need to write this by yourselves. Instead of copying straight from the slides, it would be meaningless. You need to recall the design of the flowchart and think about how to drag out the building blocks. When you get stuck, you need to think back. During this basic exercise, you need to familiarize with this. Once you are familiar with this, it will be easier for you to understand more advanced exercise. Let's take a look at this program and flowchart slide. First, we'll follow the flowchart. When organizing the flowchart, our program will get bigger and bigger. Before we start writing the program, we must first draw out the flowchart. Why? Once your logical thinking is clear, it will be easier when you write your program. When we're writing our program code, we must first determine the order of our flowchart. What will the decision of the order be based on? It will be based on the task we need to perform. For the case of our first exercise, there are two main problems to solve. The first one is that we need to give the vehicle a power switch. The second one is that we need to make the vehicle move forward and it must stop at a black line. When writing the flowchart, we need to solve for these two questions. Let's have a look. The first part is for the power switch. When this power switch is true and is activated, it will move down. If it doesn't activate, our vehicle will remain in the stop status. This first section is more or less completed. This power switch is controlled by our smartphone, so we need to set the smartphone to become an AP. Once this AP is set, we will have a switch here. We're using a switch block because we need an on and off setting. It's easier this way. We'll select switch. It will have two path options. When it's true, it will move forward. When it's false, then it will stop. There are two paths, so the if-else structure will be used. When the power switch is true, the sensor will be activated. Our digital pin, which is the infrared sensor, will be connected to the D6 pin. As it moves forward, it will start to evaluate if it's encountered a black line. When it encounters a black line, the radius will be 1, so it will be true, and it will stop. If it doesn't encounter a black line, what happens? If it doesn't encounter a black line, it will move forward. When it's false, it will keep moving forward. The program code should be written this way. You can take a look at this. When it encounters a black line and it's true, then it will stop. When it's false, it will move. Once it goes through this round, it will go back to the beginning and take turns because we've written this as a loop, so it will repeat the execution. Here, we'll begin using subroutines. It will be easier to understand when we write using subroutines. You place this line in here. You still need to think about it, but if you use this move block, it will be easier to understand using subroutines in the writing of the code. we will improve its readability. After we've uploaded the program, we'll perform the connection to the network NICs. We'll open the AP and connect to RC66. Once connected, we'll open our browser. We'll choose 192.168.4.1 and refresh it. Let's take a look at this. Once the vehicle is connected, we'll put it in place. We'll turn on our power. The vehicle will move forward. When it encounters the black line, it will stop immediately. When we bring back the vehicle, it will move forward. The power switch is activated. So remember to turn it off. When the car is connected and put in place, we'll turn on the power and it will move forward. When it encounters the black line, it will stop immediately. When we bring it back, it will move forward. The power switch is activated. So remember to turn it off. When operating the vehicle, even though the program is written in the same way as everyone else, why does your vehicle move differently from others? We can think of some of the problems. You can begin by thinking about the input. The first one is whether the sensor data we are sending is correct. There are two kinds of sensor data. The first one is whether there are issues with the hardware. The second one is whether our data has been successfully transferred to our machine. Let's check the first one and see if there are any problems with the hardware. Let's have a look. When my infrared sensor is in the white area, the light should be turned on. It is 0 at the white area, so it should light up. When it is at the black area, its reading will be 1. So the light will turn off. When you're doing the infrared sensor tracing, remember that you must calibrate it so that the reading will be 1. When it's black, and it will be 0 when it's white and the light will turn on. So pay attention to these two parts. When operating this, remember to calibrate. How is calibration performed? It's through here. Take a Phillips screwdriver. To adjust the variable resistor on top, you can turn this to adjust it. Until its motion is normal. This is regarding the hardware. Next, let's see how to deal with the software. Regarding the software, we can check the reading obtained from the infrared tracing sensor and see if the digital data is correct. So we can open the page wave editor and there will be a display block. We will compile the reading. We will copy this reading. We'll move this aside, add an adapter from the communication group, and place this on. Let's move this aside to avoid clicking on it. Now we can obtain the readings from D6. We'll name this value and add IR, which refers to the infrared sensor's reading. Then press enter. Next, we can upload this. When the program is doing this, it doesn't interfere with the original function. But we can use this mode to check if the obtained reading is as expected. In addition to using the hardware, such as the LED light to confirm, we can also ask the program to send the data back, where Going to operate this part next. Let's have a look. Once we are connected, remember to refresh the page, because we added a part where we can see the reading. Let's zoom in. This is the reading from IR. If we place the vehicle at a white area, its reading will be 0. If we place it at a black area, its reading will be 1. With this, you can confirm that the reading obtained from the infrared sensor is as expected, both in hardware and software. So this calibration should be performed in advance when writing the program. If you do it afterwards, and a problem occurs, you can use this method to check whether there is any problem with the infrared sensor. We'll remind you of 2 things. First, don't bend the map used for tracing, or it will cause an uneven surface which will affect the reading and be unstable. Secondly, it is recommended that invisible tape is used at the 4 corners of the map, or use tapes that do not leave behind any residues. It can also avoid the surface from undulating. That results in the wrong assertion of the readings, so we recommend these 2 things. Our next topic is to move back and forth between 2 black lines. We want the vehicle to move forward. After it encounters a black line, it will turn 180 degrees and move back, then turn another 180 degrees and move forward, and continuously move back and forth within the area inside the black line. Let's see the order of this program. Let's see how this program should be written. Let's take a look at this. Suppose we want it to turn 180 degrees and move. The difference with the previous program is that after we detect the black line, what we would do next is to modify this section only. We need to modify this part, which originally was only to stop. When it encounters a black line, the step where it stops still needs to be done, but we need it to rotate in place. That is, both wheels need to turn in opposite direction to make the vehicle rotate in place. The key point is to rotate 180 degrees. So we need to test out how much delay time it requires to rotate in place. Let's see how we should write this program. Let's take a look at how we do this part. First, we will open ArchBlock. After that, we'll plug the USB cable into the vehicle and upload the program. Once the upload is complete, we'll take a look at the vehicle operation process. We'll reconnect to the board and refresh the browser and press to activate. we can observe that each angle of rotation of the vehicle is not very big. It's about 20 degrees. We need to turn 180 degrees in total. Our current rotation delay time is 200 milliseconds. So we can roughly estimate if we are turning 20 degrees now, and we need to turn 180 degrees, we need to multiply this time by 9. Let's give it a try. We'll stop this first and modify our program. The part we'll modify is this one. The delay time was 200 milliseconds. Let's say we change it to 1800 and press. Enter. We'll upload the program. Once the upload is complete, we'll reconnect with the board because whenever we perform an upload, it will get disconnected. And we need to reconnect. Let's unplug the USB cable. After unplugging it, let's have a look. We'll refresh the web page. The angle is too much, and by a lot. Existing almost 180 degrees. Let's make it stop. This means that we input too much in the program. Let's have a look at this. If we need to test it like this, every time we run the program, it's quite inefficient. Do we have a smarter way to make it faster instead of having to test it every time? A parameter is changed, which is a waste of time. Life is short. We don't have that much time to test it, so we can use a smarter way to do this. We don't write a delay time setting inside the program. What should we do? We'll use the web browser to set this up. In previous classes, we learned about a slider, using a sliding bar to adjust our time, which can be faster. Let's see what we should do next. We'll remove the original delay time. We don't use this. We'll set a variable for it. We'll use a slider from the page web editor. Previously, we used 1800 ms for our delay time, and it almost turned full. We can estimate that the time will not exceed 1800 ms. Since 1800 ms made almost a full circle, so we will say 1800 as the upper limit. This is a design value for our delay. We'll name this time. And what is this for? It is for delay. So we'll add the name DELAY and press enter. We'll move this down. Next, we're going to set a time variable. So we'll set a constant variable. We'll also set a name time for this constant variable. Time, T-I-M-E. We'll place this in. Here is something important to remind you. to pay attention to. If we want to set the time for this slider, when we are giving names to the components on the website, such as push button, switch, slider, etc., the names cannot be identical to the variable's name. What I usually do is to type the components used in a web page in capital letters to avoid repeating the names. Otherwise, errors will occur during compiling. It will not find that there are two same things, so you need to bear this in mind. We've set a variable and named it time delay. We'll also copy and move this delay time over here and upload the program. Once the upload is complete, let's take a look at the operating procedure. I still need to give you a small reminder here. When you're unplugging the USB cable, please do not shake it sideways. Even if it's hard to unplug, you can slightly press down on the board. But avoid touching the metallic part. Hold it down from here and pull out the plug horizontally with force. And by no means shake it side to side, because the USB port will get damaged. Let's reconnect. Once connected, we need to refresh the browser. Now we can configure the time delay. I will zoom in so that it looks clearer. We're going to need this to be around 1100. Let's set this to 1100. We'll zoom out and operate this again. We'll start from here. The delay time is still too long, so we'll shut down the vehicle first. Over 1000 is too much. We'll adjust to a lower value to 777 and start again. See, it's working perfectly. We've completed this after only 2 tries, and it's easy to make modifications right away. So we can use the web page to adjust the slider directly and make more precise control of the rotation angle. Give this exercise a try. Use the slider on the web page to control the delay time. Once you're finished with the practice, we'll move on to the next exercise, which is the following. To move back and forth between black lines once and a stop. What does this mean? The vehicle should move forward. It encounters the first black line. It will turn around and move back. It encounters a black line and it will stop. Let's see how this program should be written. We'll begin with the flowchart to explain the concept. We want this vehicle to move back and forth once only and a stop. Here we have the concept of performing an action once each. In our program, there's a concept called counter, which can record the number of times of an action. We want to perform each action once, going to start with something called count requirement. For our count requirement, we'll set count to record the times. We'll move them. The power switch is the same as before. It will stop if it's false, or move on if it's true. In the beginning of true, we need to state a counting number of 2. What we mean is to count once here, and a second time here. So we need to set a counter. Once the counter reaches 2, it will stop. For count double equals 2, the double equal sign means whether it is equal to. This is what it represents. Next, you will ask whether the counter is equal to 2. If it is, then it can stop. Notice this, can we just write it with one equal sign? No, we cannot. Equal is used to assign values, and it is not asked whether it is equal to or not. One equal sign is for assigning values. If I write count equals 2, it means that a value 2 will be assigned to count. These two signs have different uses. Let me remind you of that. It will ask how many times it has turned. We start counting from 0, then 1, then 2. So we can keep moving down. The next section is the sensor. And similar to the previous code, it follows the same logic. The infrared sensor will be activated and immediately detect whether it is in the white area or in the black line area. The black line area, if it is in the white area, then it's false and keep moving forward. If it detects a black line, the first thing to do is to stop. Then it will rotate with a delay, which can be configured through the web page. Every time rotation is performed, we need to register a count. You can see an equal sign here, which means it's assigning, and it's different from the double equal sign above. Count equals count plus 1, which means that the result will be assigned after calculation. The equal used here should not be considered a sign, because it's not equal. Simply look at this statement. Itself cannot be equal to itself plus 1, so it doesn't mean equal. The equal in programming doesn't mean equal to. A single equal means to assign. If there are 2 equal, then it means equal to. When it's finished, we will go back to the top and repeat this action. Pay attention to this. The initial declaration will not be repeated, so we'll perform what's below that. Let's take a look at the program code. Let me remind you that the formatting of the count value cannot be performed every time. It can only be performed once. We cannot reset it to 0 every time, or it will never reach 2. Therefore, when writing the program, we must use a setup block to configure this, and then use loop block for the loop portion. This way of writing is the correct one. Let's take a look at the program code. It's basically the same as what we did previously. We have already included a delay time. There's also one here, the rest is fixed. It only differs in this section. This part is used to add a number count when the rotation is met and is ready to move. We'll continuously add up 1 when the counter reaches 2. It will go back and evaluate and notice that there is a problem and it cannot perform this action. After uploading the program, what we will perform next is to check if it has a counting effect. First, when we get connected, we need to set a delay time. The delay time for each vehicle will be different because the characteristics of each car varies. Let me ask you a question. Will the delay time be the same for vehicles with the same characteristics? The answer is no. Why? Because during its operation, the vehicle has a characteristic that will continuously change. Which one is it? Correct. It's the battery we're talking about. The battery's voltage will decrease as operating time goes on. When the battery's voltage is just charged, and is 8.4 volts, the voltage is relatively higher. The motor speed is proportional to the voltage. The higher the voltage, the faster speed of the motor, as your battery's voltage keeps dropping up to its lowest at 6.6 volts. Before charging the battery, the motor speed has dropped drastically. With a different rotational speed, the required delay time will also be affected. So you will need to pay attention to this setting and think about the difference. Next, we can have different setups for the delay time. Let's perform the counting action. We are pressed to start. It has stopped after 2 times. Let's turn this off. Let me demonstrate an incorrect case. I will press once to start. When is the vehicle not moving? Let's check the network connection. It is still connected to RC66. Why is this happening? The vehicle itself has already counted up to 2. So it will not keep going. This is the way we set up this. You can try this out. Let's move on to the next part. After we are done with the practice, please think about this following question. Suppose our count is set to double equals 2. For the evaluation of this value, if I change the statement to list 2, will it mean the same for count greater than 2 or count greater than 1? Which one of these two will have the same? Meaning as double equals 2. Let's give it a try and put these statements into the evaluation part. For assertion, the original double equals 2 will first be replaced by count greater than 2. Let's operate this. Assuming count greater than 2, count equals 0 is the same. It moves down. Second, count plus 1, and it will be 1. Is 1 greater than 2? It's not. So it's false and it moves down. We keep adding to the counter and it becomes 2. We'll go back here and ask, is 2 greater than 2? It's not, so it's false. And it will perform a third run. It moves down and the counter will be added up to 3. Is 3 greater than 2? Yes, it is. So it will execute a total of 3 times. We will try the next one. Let's move on. If the condition statement count double equals 2 is changed to greater than 1, let's have a look. The initial value of count is 0. So for this statement, the evaluation yields false. So it will execute once. After executing it once, the counter will add up 1. So it will change from 0 to 1. Then it goes back to the statement. Is 1 greater than 1? Of course it's false, so it will execute again. This time it will become 2. It has executed 2 times. And after count becomes 2, it will go back and ask again, is 2 greater than 1? Yes, it is. Therefore, it will stop. As said earlier, when count greater than 2, it will execute 3 times, and when count greater than 1, it will execute 2 times. As seen from this 2 statements, the statement count double equals 2 is the same as the statement count greater than 1. They both have the same meaning when writing the program. Hello everyone, let's practice the next application. Now we want the vehicle to move around the oval-shaped black line. Let's take a look at the actions they will be performing. Let's have a look. We want the vehicle to circle around along this black circle. We don't want the vehicle to exceed the area. We will set the infrared sensor to perform a tracing action inside the black line. During the tracing, you can see that the infrared sensor is located here. We want it to encounter trace the white section and look for black. When the infrared sensor traces black, it will want to move away from black. It will continuously use this method. If it's white, it will move towards the black line. When it is on the black line, it will move in the direction away from the black line. We can use this method to trace the black line and move around the circle. Let's take a look at this. Let's take a look at this. We will set up a power switch. Before the power is turned on, the vehicle is idle. Once we turn on the power, it will be true and the vehicle will move forward. Since it basically has only one motion direction, so we will set up a direction change here. It doesn't have the option to move backwards, so we only need to set it up to move forward. As for whether to move or not, we can use the analog pin to set up this part. Next, let's have a look. As the vehicle moves forward, our sensor will start working and check if the vehicle is in the black area. As said before, we need to check if the vehicle is on the black line. If it is, it will obtain a true reading. Obtain a true reading, which means it's on the black line. So it needs to move away. It needs to deviate to the left. When the vehicle is in the white area, what will happen? The vehicle is in this position. What will the vehicle do? It will want to move towards the black line. This time, we'll perform a right turn. Let's take a look at the second evaluation in our program. Because the first if-else block is used by the power switch, let's take a look at this part inside, which is for the infrared sensor. When this is true, it will move away. We're moving along the inner side of the line. Moving along the outside or the inside is different. We'll be moving from the inside, so we know that we need to move in a clockwise direction. So for this part, we want to turn right. If the vehicle is located in a white area, because it needs to approach the black line, so it needs to turn left. Let's take a look at this. Since this is written using subroutines, you should be able to see the difference. There's a special part here. We will set the speed to 500. We'll set it to 500 for now since you are not used to its control yet. After you are familiarized with it, for the next stage, you can try then change the power to a slider. After we've managed to move along the oval line, what if the line segment on our path is not continuous. How do we solve this kind of problem? Let's have a look. We have the same program and the same oval. The oval is broken off. Let's try walking through it and see what problem will happen. Let's have a look. We'll use a smartphone to control the vehicle. Let's begin. It will turn outwards. What is that? It's doing the same. It's our flowchart. When it's in the white area, what will it do? It is at a broken segment, which is white. When it's in the white area, it will tend to move towards the black area. So it will turn like this. For this topic, we will need to solve this situation. How do we solve it? Let's keep on looking. How do we solve a situation like this? Our solution is like this. How do we solve this situation? Our solution is to add another infrared sensor. Why do we need to add another infrared sensor? The reason is that when we encounter white, we only have one choice, which is to move towards the black line. For a situation with only one choice, it's hard to evaluate, so what should we do? We'd add another sensor to assist, having two options. To assist in the evaluation of whether it is a broken line or it is moving away from the black line. We're going to do this part. First, we're going to install the second infrared sensor. We'll do the explanation after the installation. What does it mean? Why can we have an assistant for evaluation by adding a second sensor? Let's take a look at how we're going to add another infrared sensor. This one will be used as an assistant for evaluation. We'll take out a screw and nut. We'll use a 12 mm screw, then wooden gasket made by laser cutting, as well as infrared sensor with a 30 cm long DuPont line. A 25 cm line is also acceptable, but a 20 cm one is too short, and sometimes it would be hard to connect the wires, so 20 cm is not recommended. When we're connecting this, since our analog input part has already been used, we won't connect that part. So we'll only need to connect 3 wires. We will leave out the AO pin. We'll only connect the VCC, GND, and DO wires. When connecting this, we will all unanimously connect it to the right wheel. This way it will be easier to explain in class. Pass the wire through from the inside. You should take your time doing it and don't be nervous. Don't cause problems with its operation. There is a motor output shaft inside, so you need to avoid it a bit when doing this. It got stuck. You can grab a screwdriver to slightly hook it, but don't break any of the other wires, especially the wires of the motor that are inside. Pull this out. After pulling it out, we'll move the wire up through this place and then arrange the wires. Because this part is quite small, we won't be able to pass the wire to the top, so we'll need to unscrew these 4 screws on the controller board. The battery box must be loosened. If not, it will be hard to work with a ladder. When working with this, the power must be cut off. You should develop this habit. Don't admit it because it's just for a moment. If you're careless for one moment, you'll short circuit and burn out. So be sure to develop this habit of cutting off the power whenever you're working with wiring. We'll pass the wire through and move it up. Once it's up, you can assemble the controller board back. When screwing this, temporarily fix the 4 screws in place and tighten them after you finish adjusting the position. When tightening, take turns to tighten the screws in opposite diagonals. Don't screw it all at once and do it slowly. This screw was left on top. You can take a look from the side to help align in place, then tightening it. If you're worried that the copper pillar below is loosened, you can slightly grab it with your fingers. If some of the female students don't have the strength to grab it tight, pliers can use for assistance. Take turns to screw it in. Don't screw it tight all at once. Once the parts are almost in place, then you can screw them tight. You can have a look, it's more or less done. Now I will proceed with tightening the screws. While screwing, if you realize that the screws keep slipping, you need to be careful. You can hold the bottom part with pliers. Otherwise, it will keep slipping and you won't be able to tighten them. You must hold the copper pillar in place. This part is finished. Let's leave the wire out for now. We'll connect this part next. You must pay attention when connecting this pin when putting in the wooden gasket, because we need to observe whether the LED power indicator can light up. So we designed this with a missing corner so that it's easier to observe when the light is turned on. The light indicates when the infrared sensor is used in the digital input. Let's organize this a bit. When installing this, we'll receive this position. However, we've had students that installed it over here. Why? Because they had ideas of their own. When we arrange it like this, from here we can see that there are 5-pin holes. If you want to use an infrared tracing sensor with 5-pin holes, it's fine. You can connect a 5-pin. It depends on whether you have the need. Some students arrange the wiring like this. During class, let's say that they do not want to use the 2 in the middle and want to use the one on the far end. You should write your program according to your own ideas. You don't really have to follow the teacher's settings. If you think it's okay, then it's okay. However, during practice in the beginning, do it at least once following the teacher's idea. Then you can do it according to your own idea and figure out which way is more appropriate. Okay, let's have a look. Likewise, black for VCC and white for GND. Now we're going to do the wiring. We need to connect the pin to D0. The D0 pin is quite special. It can only do digital input, but it cannot do digital output. Therefore, when using this D0 pin, the pins D1 to D8 can be used for PWM output. Only D0 is not able to do so and can only do digital input. So bear this in mind when using it. Okay, let's take a look at the VCC and GND wiring. VCC is gray and GND is white. We'll connect them. Next, we'll connect the other pin at the 0. We'll grab a zip tie and fix this in place. There will be more and more wires. After a while, you may have to remove these old zip ties and tie new ones. It's good for now, so I won't remove the old ones yet. The more functions we have, the wiring becomes more complicated, and organizing the wiring becomes an even more important task. Secondly, it is easier to check. We mainly do tasks such as avoiding obstacles or move in a maze. If the wires are too long and accidentally get pulled off, it will cause errors in the sensor's actions, so you must pay attention to this. After tightening, with a zip tie, we'll use pliers to cut off the zip tie excess. We're done with this part. Let's take a look at this. I've already explained to you earlier why we need an auxiliary sensor. The original sensor is used for tracing. One sensor is enough for tracing a continuous line. However, when there's a section that is cut off, or profiles that are not that simple, there's no way to evaluate. Therefore, we need to add an extra sensor to assist in the evaluation. And you still haven't figured out its rule changes. We can make a table like this. How will the sensor's readings be when the vehicle is on the black line, when it's at a broken segment, or when the body is deviated left, right, or in the middle? You can give this a try first. You can estimate how the reading will be, or test it out for real, using the vehicle. After verifying the result, you should be able to figure out the pattern and complete this table. Once the table is filled in, we'll figure out what its pattern is. Let's take a look at this first. We found out that if one of the sensors is still at the black area, it means that the vehicle is still on the black line. The sensor hasn't reached the segment that's broken off. If one of the sensors have a rating for black, it means it's still on the line. If both are white, regardless if it's deviating to the left or right, then it's definitely in the broken segment. For this situation, we can choose whether it is the left or right sensor, mainly responsible for tracing, while the other one will be used to assist in the evaluation. Let's take a look at this. Next, we'll do it simple first, and then make it complete. What's considered simple and what's considered complete? We need to add two things at the same time. The first one is to add a sensor, so that it becomes a dual infrared sensor. The second thing we need to add is the part that evaluates the section that's broken off. If there are two problems that need to be addressed at the same time, I suggest that you don't write it like this, because if a problem occurs, it will be hard to find out which one is responsible and correct this accordingly. Let's start with the part that we're more experienced, which is using two infrared sensors for tracing. After we've finished the part for using two infrared sensors for tracing, and there are no problems, then we'll move on to dealing with the broken segment. It'll be easier this way. Don't try solving two questions at the same time. I'm already familiarized with this. I grew up with programming, so it won't be a problem for me. If you're still beginners, I recommend that you tackle one problem at a time and don't try solving everything in one go. Now that we're using two sensors, I'll be teaching you another logical evaluation. For example, here you can see an AND, and what does AND mean? It has the same logical meaning as in mathematics. AND means that both statements need to be established. For it to establish, both need to be 1. For it to be true. For OR, as long as one of them is true, then it's true. Not is the opposite. What does that mean? When it's not, then 1 becomes 0. And if it's 0, it becomes 1. we will be using frequently in our upcoming classes, so I'm letting you know about it. Let's take a look at this flowchart. Likewise, we included a power switch, then we'll move down. After the power is turned on, for this next section, we'll divide its motion. If the left sensor is 1 and the right one is 0, then we turn left. When both sensors are 1, it means the vehicle is on the black line. If the left sensor is 0 and the right one is 1, then we'll turn right. This setting will be the same as what's shown in the table, which follows this pattern. When the car deviates to the left, I need to turn it to the right. Try writing this program. Before writing it, we installed a new infrared sensor, so remember to perform calibration. After calibration, we will begin with the software design. For the hardware, we need to check whether the rating of this newly added sensor is working correctly. Let's take a look at this. When it's in the black area, the LEDs of both sensors are turned off. If it's in the white area, both LEDs are lit up, so there should be green lights showing. The same goes for this. If it's in the white area, this will show a green light, and this other one doesn't. For this case, this one in the black area, so it doesn't show the green light, and this one in the white area shows it. You can check this first. And if all is fine, we'll continue with the writing of the program. Before writing the program, we need to finish with calibration. Let's move on. We've written the program code based on the flowchart. Let's take a look at this. We have added this AND logical operator in here. This means that both conditions must be made. For these overall conditions to be fulfilled, both conditions need to be true in order for this to be established. What if it's 0? That's why we introduced you to the NOT operator earlier. If you use NOT, then it's reversed. If the rating is 0, it becomes 1. When passing through the NOT operator, you can use this method. According to this flowchart, when left double equals 1 and right double equals 0, it will turn left. The left and the right turning are configured this way. On the side is the writing of the subroutines. Let's operate it. Let's move on. We've written the program based on the flowchart. Let's take a look at this. We have added this AND logical operator in here. This means that both conditions need to be made. For these overall conditions to be fulfilled, both conditions need to be true in order for this to be established. What if it's 0? That's why we introduced you to the NOT operator earlier. If you use NOT, then it's reversed. If the rating is 0, it becomes 1. When passing through the NOT operator, you can use this method. According to this flowchart, when left double equals 1 and right double equals 0, it will turn left. The left and the right turning are configured this way. On the side is the writing of the subroutines. Then let's operate it. Let me also explain this part. In addition, we can add another function to send a feedback of the values. In case you need it, you can do it this way. Once our program is uploaded, we'll use the web page to control the vehicle's actions. Let's tap to begin. It looks like the two working sensors are working normally. Again, the broken segment hasn't been solved yet. What we'll be doing next is to write a program to correct the problem of the broken segment. Before we begin talking about this, for the motion part performed, although we've already calibrated the sensors, that is part of the hardware calibration, the software also needs to be calibrated and see if the reading sent in is normal. I suggest that you make a display to reading both readings from the left and right sensors. Let's move on to the next step. We need to add a part for the broken segment. Suppose we have a broken segment. How should we correct the program? It is this section. Suppose both sensors have a 0 reading, which means it's in the white area. We need a few seconds delay. It only moves in a straight line, so this AND logical operator line must be added in here. Both of them are 0, so we'll add a NOT operator and execute. You can try and add in this operator. Likewise, for a display section, the reading from the infrared sensor is read in. Once the program is finished, we will upload the program. Later, we will test the broken segment condition we just added, which is written here, and we'll follow up with move, which refers to the action of moving forward. We've added, in a web page, the display of the readings obtained from the D0 and D6 pins. Once the upload is complete, we'll operate it for you to see. Let's move on. The readings are shown here. Let me zoom in for you to see. These are readings obtained. Next, we'll turn on the power and place the vehicle on the line. We'll begin. As you've just seen, when it encounters this white area, it will keep moving forward. The line we added for the evaluation of the broken segment, it has moved forward as expected, and there was a delay. The delayed and continuous action was shown. This means that the program is working normally. You can give it a try and run this program. After the program is finished, here you notice anything during the operation. When the car is in the white area, both infrared sensors are detecting white. So the vehicle will have a delay with the moving action. The length of this delay will affect its crossing of the white area. Remember that we used the slider to modify the delay time for extended action. You can add this method to optimize the operation of your program and make it more precise. Try modifying this program. The next exercise that we are going to do is this. There's a white line area and broken segments. What if there is a black cross line? The thinking strategy is the same. We will write down all the situations and find out which parts will be different. Then write down all the possible rating scenario for infrared sensors. Afterwards, we will figure out its rule. After obtaining the rule, then we can write a program. Use the method from the previous exercise and try to find out one of the rules that can be used as evaluation criteria in the program. You can try and do it. Let's fill in this table. This is the same as what we did in the exercise with a broken segment. We list all the situations that we'll encounter. Once you finish this table, have you noticed something? The ratings obtained from left and right sensors for the black cross line is the same as when the vehicle is centered on black line, when the vehicle encounters a black cross line. Is there a need to modify the program? The answer is no, because it yields the same result as when it's moving center on the black line. So there's no need to correct this. In other competitions, where cross lines are present, you will be required to modify the program. But we don't need to do it for this case, so you need to see what is needed for each case to write the evaluation criteria of the program. We did not modify the program at all, and we will use the program used for a broken segment to operate it once and see whether this black cross line has any impact on our program. The answer is that there's no impact because both sensors are getting readings for black. So it will continue to move forward. So no modification needs to be done, and it can perfectly pass the cross line section. You can try and verify whether the program is working as expected. When it encounters a black crossed line, it will continue to move forward and finish the original setting. Hello everyone, what we are going to do now is the analog input signal. We already have a basic understanding of the application of digital signals. Let's now talk about the difference between the analog input signal and digital signal when it comes to vehicle tracing. Let's have a look. What's the difference between analog and digital in terms of vehicle control? When using digital signaling, such as in this case scenario, when the infrared sensor is at a white area, fixed speed difference of the wheels to turn to approach the black line and correct its path. It's the same when it is on the black line. It uses a fixed speed difference of the wheels to run and move away from the black line. However, the motion using analog signal is special in the sense that its reading is between 0 and 1024. So if we assume that it's at halfway of 1024, which is 512, it is right in the middle between the black line and the white area. The closer your reading gets to 512, the closer it is to a center line. However, if it is at extreme readings of 0 and 1024, then it means that it is far away from the center. So the further away the value is from the center line, what can we do? We can make the speed difference even larger, but if the vehicle is close to a center line, then the speed difference between the two wheels doesn't need to be so big, and its swing and correction are not too big. What help is the motion using analog? The whiter it is, the slower the right wheel becomes. The less white it is, which means it is closer to the center line. And the right wheel only needs to be a bit slower, and it doesn't need to slow down too much. Their speed differentiation will be more than 1. It will be based on how close or far with respect to the center line to make adjustments. The same goes for the black section. If you are using analog for the vehicle's motion, what happens when its motion is close to a center line? The amplitude of its swing is relatively small. Its zigzag movements are small. This is the advantage of analog over digital. We'll first read in the analog reading and perform its evaluation. First of all, we need to confirm the value for a reading when the vehicle is at the center line of the black and white areas. What will be the value obtained at the center line? Measuring from white to black, the reading should range between 100 or so and 1024. So we'll define 600 for the center line. You can set the value that you want. We'll use 600 as a reference value. If it's smaller than 600, it means that it's in the white area. If it is greater than 600, it's in the black area. At this stage, it's still very similar to the motion using digital signal, but as I told you before, whenever we are writing a program, we should not make a lot of progress at once, but should write it slowly. We make sure one variable is correct. Then we continue towards more in-depth changes. When you are not familiarized with programming, we do this step by step. When you are familiarized with this, you can perform all the things all together. It doesn't matter. Let's take a look at this flowchart. Let's take a look at this flowchart. In the same manner, we will first include the control for the vehicle to move or stop. After it starts to move, we need to have a sensor to measure its reading. According to this reading, in this case, there will no longer a difference between true and false. The difference will only be whether it's larger or smaller. As said earlier, our reference value will be set to 600. This value will depend on the actual testing of your vehicle's center of gravity, which should be around 600. If it is greater than 600, it means that it is closer to the black area, so we can make it move away. If it is smaller than 600, it's closer to the white area, so it needs to get closer. Let's take a look at the following program code. The difference is that we'll need to reading the analog reading first. Also, we'll have this section added. We can use power to control it. We can adjust our power output using a slider. We'll increase the power output. At the beginning of the practice, we'll set it up to 500 to be more stable. If you set it to 300, the vehicle probably won't move. Why? Because if the PWM is given too little power, it won't be able to overcome the maximum static friction and the vehicle won't move. But it shouldn't be too high either. If you can't actuate the vehicle at a low power, you'll make some noises. So you should not continue with that step. It'll make it move or let it stop. So you must pay attention when doing the power output. Next, we'll display the readings obtained in our smartphone. And you'll be able to see the value of the analog readings. This has been practiced before. We'll place that into this program. Please write the same method into the program. This way, it will be more convenient to detect any problems. We need to evaluate the reading that is sent in, which will be done by this section. This if-else is in charge of the reading evaluation. That's why we mentioned we'll set the centerline value for the vehicle to be 600. When it's greater than 600, it means it's in the black area. Let's test out our program. We'll zoom in a little and look at the smartphone. We can see the analog reading from the infrared sensor. Let's test out the sensor from the middle to do an analog reading detection. For example, black is 1024, and if we move it towards the white area, the reading is about 184. The smallest value probably won't exceed 100 because at its lowest, there's still a bit of voltage present. So it will give some readings anyway. It will never really get to zero value. Later we'll be using this analog infrared sensor for tracing. As said before, don't let the speed be too slow. We'll adjust it to around 500. To be more appropriate, let's start this up and see how it moves. You'll realize that its range of motion still resembles the digital method. This is because currently, it's only referencing the analog reading but with motion using digital. Because it still can't difference the different levels. Let's move on and see how these different levels are written for the motion using analog tracing. You can try this out yourselves. Reading the analog reading, then perform a simple evaluation, and make the vehicle move along the black line. Once you're done with the operation, let's move on. What we'll see next It's a difference in the use of analog and digital input. The reading has already been sent in, so we'll check the difference next. Let's take a look at this picture. We'll have a brief explanation. The direction of the arrows represent a vehicle moving forward and backwards, while the x-axis represents the digital reading from the infrared sensor, so there is only 1 and 0 states. The red line represents the motor's power output, which refers to the degree of rotation. We'll use the infrared sensor to determine the motion of the vehicle. When it's either 0 or 1, it will perform a turning action. When turning, the speed difference only has one status, which is one wheel is stationary while the other one is moving. The same goes for the other side. The power output is fixed. It will not make adjustments according to how close or far away it is from center line. This is different from analog reading. It will be a slope line. What does this slope line mean? The larger our reading is, the greater the distance with respect to the center line, and the greater the degree of turning is required. The advantage of this is that if you're only a bit deviated, then you only need a small adjustment, so the motor's power output will be smaller. However, if the deviation is large, and the farther you are from the tracing target, the larger the degree of adjustment, and the greater the motor's power output will be. This is called proportional control. The greater the margin of error, the greater the PWM output will be. So it's proportional. Next, we'll take a look at this. How are we going to perform this when writing the program? Next, we're going to write this program code. First, let's talk about how we're going to perform this. Let's take a look at the analog reading range of the infrared sensor. Its lowest value is at least 100, so we'll say 100 as the lower limit. The upper limit value is 1024. Suppose we don't turn and only move forward, we'll assume the value for moving toward to be 612. If the infrared sensor reading is at 612, then it moves forward without any turns. If it's larger than 612, then it will need to start steering. A speed difference needs to happen. In the beginning, when it's at 612, the speed difference is small. However, when it's close to 1024, I need the speed difference between the two wheels to be large. One wheel is basically stationary while the other one moves at full speed. How do we do this part? This can be performed using a function called map. For this map command, the reading that's measured is from 0 to 1024. Then it is converted to the motor's power value. I'll tell you how to set out this target value later. The application of the map function was explained previously. It can map a certain value range to another type of range. It will be mapped proportionally. Let's take a look at this program code. This program was modified from the previous program. We'll divide this into two halves at if-else. Part of this is for when it's larger than 612, which means that it's in the black area. This part is when it's closer to the white area. The logic for these two are the same. Let's first take a look at the black area. When it's greater than 612, I need to turn left. And correct left wheel. The right wheel is fixed because it uses a constant speed. I will adjust the left wheel. The left wheel's power output will be like this. When it is at 612 or close to it, it means that it's still at the black area and close to the area for moving straight forward. It is close to the black and white area. There's not a big difference, so its speed is pretty much the same as the right wheel. As it gets closer to the black area, the reading becomes larger than. It means that it is moving further away from the center line. We will require a greater speed difference, so that the speed and turning are bigger, so it approaches 0. The method for the white area is the same. When it's close to 612, there's not much difference in speed, but as it gets whiter, the lower the reading becomes. So I want to increase the speed difference. The way this method works is, the greater the error, the greater the speed difference. This is how it works logically. You can try and write this program. We'll later see how the effects of this program will be. Once we have finished writing the program, we'll use the map function to correct the past margin of error. Our speed will be adjusted according to the error value. Let's take a look at this. After we are connected, we can measure its reading. The number at the top is its reading. We can set out its rotational speed. In the beginning, we'll set its speed to 500 and start it up. You can see that its swaying will be milder because the error value is not too big. So its adjustment will be in a smaller degree. We'll increase its speed and check its result. As speed increases, the degree of swaying becomes greater. Yet it's still able to adjust itself back. You can clearly see that the analog method and the digital method is different. The speed difference will not be a two-stage variation. It will adjust the wheel speed difference based on its current situation. It has already gone out of control. Why did this happen? Because when the deviation is too big, it cannot turn back enough. How do we fix this? You can try to think about a solution. I'll present my own idea, but try it based on your own idea. Now that we've reached to this point, as I told you at the beginning, when we're doing this kind of project-style production, when the problem becomes bigger and more complex, you have to think for every scenario. What's the possible cause for this problem? We can propose our possible solution, and then verify whether our solution can really solve this problem. This is the real challenge that we must face in these project-style productions. How to come up with your own ideas to solve unknown problems. You can record your process and write it down in your engineering notebook. Since our vehicle got out of control and went outside the black area, let's correct this. Let's take a look at the program that we wrote. What is the result after its execution? You're probably writing your own program. You can check with the result and compare them with the teacher's program. See what the difference is between them. When you're writing a program, there's no standard answer. There's only a better answer. Why do I say it like this? As long as your solution can solve the problem, then it is a good solution. Whichever solution has a greater effect, then that solution is a better one. There's no standard solution. Let's execute it. We'll set the speed to 500. We'll increase the speed. You'll see that the swing is bigger than last time. I will adjust the speed to its maximum. Because it lost control at its maximum speed, so I will adjust this to 1024. The swaying motion is bigger than before, but its deviation from the black area is smaller, and it will immediately adjust itself back. The correction speed is better than the previous method. Let's see what the difference is in its writing. The difference is in here. I've divided the map function into two sections. We originally had 612 to 1024. Now I've added an 812 in between. What does this mean? What do I want it to do when it's at 812? I want it to do proportional control. When it exceeds 812, once it exceeds this range, what will it do? The speed difference between the two wheels will be its largest. I will make this wheel to remain stationary. Once it exceeds 812, I feel it's risky, so I want it to make an extreme adjustment instead of proportional one. When it exceeds 812, its swing will be very big. The swing we just saw is different from above. When we're doing analog control, we'll need to adjust the point where we want proportional control, according to our surface curvature. How do we adjust the range of the proportional? That will depend on the variation of the following graph. We've used these two methods for your reference. Suppose you want to use analog control. How do you perform its control? Of course, you can choose not to use map and use other mathematical functions instead to do the conversion of the error value, correction amount. As long as it provides a better effect, then it's considered a good solution. You can practice a bit and then we'll move on to the next topic. Once you've tried using the analog method, let's move on. This is what we are going to do next. The situations we encountered earlier were quite normal, with only one black line, so we only needed one sensor. However, if we add a white area and a cross area, one sensor is not enough to determine the situation. Therefore, we need to add another sensor, since the node MCU only has one analog pin. So the other one must use a digital pin. Let's take a look at this. We've talked about how evaluation works before, so we will not talk about it here. You can go back and review. Let's take a look at this. We'll divide it into two sides. The analog will be used as the main sensor for tracing. The digital one that was added will be used to assist in the evaluation of two situations. The first one is when it encounters a cross line or a light gap. How will you assist in the evaluation? First, let's take a look at this front section. When the analog sensor encounters a white reading, the first situation would be that the line is broken off, so it needs to proceed the broken line situation. If it's black line, then it's alright. It will continue with the tracing and there's no problem. The point is when it is white area, both the main and auxiliary sensors have a white reading. What does it mean? It's in white area and needs to move forward with a delay. So let both wheels move forward with a delay. On the other side, if it's in the black line area, one has black readings, while the other one has white readings. It means it's moving further away and it continues to do the tracing. If the auxiliary sensor also detects black, then it's alright. Why? Let's double check. It is in the straight line area, so it moves forward. This is the first possibility. The second possibility is that it has moved toward a cross line. It will continue moving forward, so there will be no problem. This algorithm is performed this way. Let's take a look at this. Later, when writing the program, we will only deal with the section. This remaining section will be up to you to complete. You can try it yourselves if you've written similar code. You can try writing this yourselves. What have we added for this part? We've added something for the white section. Let's look at the previous flowchart. We are executing the white section. When the analog sensor detects white, let's see how the digital part will evaluate. Okay, let's first take a look at the analog rating. The analog rating will be evaluated when it's larger than 612. What does it mean? It's at the black area when it's larger than 612, so it will move forward. When this block is true, it executes this. If it's false, this section becomes the white area. The analog rating will be processed at this section. This light D rating will be used for assistance. It is the digital sensor used for assistance. the digital sensor's reading will be loaded in and will be displayed in the smartphone. Let's look at the if inside. As said before, there will be an execution for true and one for false. When true is executed, it approaches the black line. Let's take a look at this. When this infrared sensor detects white, it will perform the motion for the white area. What is this motion? Check here. Both white, that is, the analog and the digital. Sensors both detect white. What does it mean? It's at a broken off area, so both motors need to move forward. When they move forward, there will be a delay time. For convenience, we will use a slider to control the delay time. This way, you can use your smartphone to determine how much delay time at the white area. If my main sensor is at the white area and the auxiliary on is at the black area, what does it do? It executes the false section to perform tracing. This program code functions like this. You can give it a try and see how this can be written. Let me show you a demonstration. You can also take a look at this program code on your own later. First, we will set the time. Initially have it between 500 and 600, not too fast. Next is to set the delay time. Don't set it too long, because the white gap is quite small. I think that a delay of 7 milliseconds is enough. Let's execute this. A delay was performed at the white area, and it kept moving forward. It went out of borders here. When a vehicle tends to get out of bounds, we need to consider our delay time. And our vehicle speed setting, this can be easily adjusted from our web page. Using the web page to control the vehicle and adjust its power output, and a delay time when it encounters a white line. We can make the execution of this program much smoother. You can give this a try yourself. You should practice the black cross line. Exercise as well. Practice a bit. Once you are finished for the problems encountered, which we were not able to anticipate, let me give you a few suggestions. The first one is that with the motor powered off, place the vehicle in the wrong path, and first observe whether the infrared sensor reading. If the reading is not in line with our expectation, then you must check the rule that you came up with based on previous observations. Verify if you made incorrect observation. Secondly, check if your sensor has been calibrated. If your readings are all normal, it means that the rule you've determined is wrong. If there's a problem with the rule, no matter what you write, you'll be wrong. If the rule is correct, the algorithm and flowchart written into the program will be correct. There should be not much problem. If this is the case, what should we do? The last possible explanation is that your vehicle's physical properties do not meet the requirement. The motor is not fast enough, or its torque is insufficient. All this needs to be thought of. Let's say that when we are performing a turn, both wheels move forward. Is it possible that radius of gyration is not big enough? Why? What we did previously was to use the right wheel as the turning pivot. What is the disadvantage of this? Its radius of gyration is bigger. Therefore, its degree of turning cannot be too small. It can make big turns but fail to make small ones. There's another way, which uses the vehicle's chassis center of gravity as the turning pivot. We make the wheels turn in opposite directions. Not only we increase the speed difference, but also make them turn in opposite directions. You can try this. If you're not able to solve this, then make the wheels turn in opposite directions to solve the tracing problem. Regarding the tracing part, we've covered enough. As for its comprehensive application, it depends on everyone's progress. You can also find some tracing maps. They are usually used in competitions, and give it a try. Hello everyone! After we've completed the applications of infrared sensor in Unit 7, we're going to talk about how the ultrasonic distance sensor can be used in applications. The ultrasonic sensor is commonly used for distance measurement. So common problems include having an obstacle in front that is anticipated by the sensor. The ultrasonic distance sensor can also be used in the walkthrough of mazes. In our following activities, we're going to let you try and walk through a maze. First of all, let's take a look at the following. This is the closed loop control used for a maze walkthrough. As input, we'll move along the wall at a fixed distance. Our sensor will measure the distance from the wall and will continuously send feedback of the error value between the expected and actual distance to the wall back to the controller. Then according to this value error, the controller will adjust the error of the two wheels, adjusting left and right, so that the vehicle can maintain a fixed distance from the wall. Next, I'll ask you to review about ultrasonic distance sensor readings, as well as the if conditional logic from the third and other previous units. Check previous videos to review these topics. After reviewing, we're going to perform a basic practice of the fixed distance action. This exercise will be the feedback control. Let's have a look. What's going to happen is that the vehicle will move forward and will stop when it encounters a wall. First of all, please complete the wiring according to this image. During wiring, please ensure that the power is cut off. We're going to begin with the installation of the ultrasonic sensor, and servo needed for the maze walkthrough will be installing it in this place, and then arrange the wiring. First of all, let's grab the screwdriver. Let's loosen the two screws at the front first. Next, you must pay attention to this. Remember to pass the servo's wire through this hole over here. Then we'll take the two screws that we just removed and put them in this place, and then screw this in. We'll screw this roughly for now. Next, we want to connect the wire for the SG90 servo at D5. There are 3 colored wires: orange, red, and brown. Red is positive, brown is negative, and orange is in the signal pin for D6. We'll connect it here. Next, we'll connect the infrared sensor. We can take a look at the top of the infrared sensor. There's a GND and a VCC. Let's connect the VCC and GND wires. VCC is black and GND is purple. Since later we are going to connect them at D7 and D8. So we'll connect this to the positive terminal of D7. And then the negative terminal of D7. There's a trick on here. We'll connect the white wire to the D7 signal pin. Echo will be connected to the D8 signal pin. Check after plugging them in, especially the positive and negative terminals. VCC and GND are the most important, so we must do a double check and ask 3 classmates to help you confirm. You must not connect it wrong. VCC is black. See which colored wire you have and pay attention to it. Ours is black. I'll plug it here in the middle. Purple is ground and will be connected here at the bottom. Trick will be connected to D7 and echo to D8. Once finished, we'll arrange the wires. We've already placed almost all the wires for the vehicle, so we'll take out a zip tie. After getting the zip tie, we'll arrange this servo wire. This wire will not be turning around. We suggest that you do not move the wire for the ultrasonic sensor. It looks ugly this way, and you can reduce the length, but we're concerned that it can get pulled. So basically, we won't do any adjustment on this wire. Now we'll adjust the wire for this servo. We can fix this wire together with the other wires. In the same manner, we'll fix the wire here. Then we'll use a zip tie to fix this in place. Cut the excess off. The wires are fixed to prevent accidentally pulling during the class and avoid unnecessary damage and errors from occurring. It should be like this. And fixing the wires. You can give it a try yourselves. This is our topic. When the vehicle is moving forward, encounters an obstacle, it will stop, remove the hand, and the vehicle will continue moving forward. Let's keep on looking. There is our flowchart, from which we will perform the explanation. Although you have the servo installed onto your vehicle, the following operation will require the use of the servo to prevent the shaking of the servo during the operation. Since it may receive signals once the program starts up, so we will turn off the power and unplug the servo for the time being. We can place the wire to the side. There's no need to remove it completely, just place it on the side. After we've operated up to a certain degree, we'll connect the servo back. When we actually require the use of it, we'll be using our hand as a reflective object. When the vehicle encounters an obstacle, it will remain stationary when its distance is less than 10 cm. Let's keep looking. Let's take a look at this flowchart. Likewise, we'll have a power switch, and the vehicle will move forward. The ultrasonic distance sensor will begin its measurement. When the distance is less than 10, it means that the obstacle is very close. If the condition is true, then the vehicle will stop. If the distance is greater than 10, it will continue moving forward and keep performing this action. We'll display the distance that is being measured, which will be evaluated here. When it's less than 10, and it's true, then it will stop. If it's greater than 10, it means that obstacle is still far away, so it will perform the move action. Let's practice this part a bit. Later, we will have the measurement result displayed here. We'll use power to control this. After we've uploaded the program, we'll open the browser in our smartphone and connect to the network. You can see that the distance measured is 19. Move the vehicle forward and the distance is shorter, which means the ultrasonic sensor is working normally. For the writing of our program, when the distance is less than 10, the vehicle will stop. So we'll turn on the power to make it move forward. It will come to a stop. We move it backwards and it will continue to move. It will stop whenever the distance is less than 10. Let's turn the power off. Let's keep moving. You can practice writing this program. Let the vehicle stop at a distance of 10 centimeters. Practice a little bit. Once you're finished, we'll continue with the next topic, which is to walk along a wall at a fixed distance. This is the first basic function we need to practice for program writing of our micro mouse. Let's take a look at the following picture. The ultrasonic sensor, which will be the vehicle's eyes, will face to the right. Then the vehicle is moving forward. It will maintain a fixed distance from the wall. Through the reading obtained by the ultrasonic sensor, it works similar to an infrared sensor. When the distance is far, then I need to find a way to make the vehicle move closer to the wall. Using this topic as example, the wall is at the right. So what should we do? The speed of the right wheel should slow down so that the left wheel is faster. Through the adjustment of the speed difference, we make the vehicle turn right. When the vehicle is close to the wall, it means it needs to move further away from it, so the speed of the left wheel should slow down. This is similar to what we did for the infrared sensor. We adjust the speed difference between the two wheels to meet the requirement of being at a fixed distance along the wall. Let's keep looking. This is our flowchart, which is very similar to our infrared sensor. First, we'll need to give it a power switch to control when the vehicle moves or doesn't. This part over here, this is the part for the power switch. The if-else part of the power switch is in here. When the conditions are met, it is true and the vehicle will move forward, as seen here. Once the vehicle moves forward, what is the next step? We need to measure the distance. If the power is off, then we remain stationary. We execute the else part. Next, let's take a look at the second if-else status included here. We need to measure the distance, as mentioned earlier. When the distance becomes larger, when the distance becomes bigger, what does it mean? This else doesn't meet the conditions, so we need to turn right. However, when the distance becomes smaller and is close to hitting the wall, then we need to turn left. Let's follow this program and practice a little bit. Let's see how your results go later. Let's test out the program we just wrote. We'll move at a fixed distance. The vehicle is set to be at a 10 cm distance. At this moment, the vehicle is at 7 cm distance. It's a bit too close, so it should move away from the wall. Let's see how it moves. It will bump into the wall. This is how it performs. In a fixed distance motion situation, you can try and perform this at higher speed. We can increase its speed with the PWM slider. See what the maximum speed that you can get is to move along the wall. After you finish practicing, did you notice a peculiar situation during the operation? The situation is this: we can measure the same distance at different orientations. Our vehicle sways during its motion, so its orientation is towards the left or the right. The distance measured will be the same, which will result in a miscalculation. For example, we said earlier that when the distance is greater than or less than 10, it will perform different actions. However, if the distance d is 10, the vehicle can detect a distance of 10 when it's left or right oriented. This will cause a miscalculation. So I will tell you how we are going to solve this problem. The method that we used is to change the angle between the autonomous vehicle and the sensor's measuring axis. We don't use a simple 0-degree angle. You have to make slight adjustments. The way to adjust this is that The way to adjust this is that I first adjust the angle of the ultrasonic sensor, which was originally 0 degrees. This angle is not definite, we'll explain more later. Through this angle, we can determine if the vehicle is moving further or closer to the wall, and the earlier situation will not happen. Of course, students who are more experienced will realize that if the turning becomes too great, it will still be able to detect the same distance, but for that to happen, the deviation will have been excessively large, and will probably be too hard to return back its original precision. For that kind of situation, we'll deal with that separately. At present, using this method of giving an angle to our ultrasonic sensor, we can prevent miscalculations from happening. Let's take a look at the following. We'll first add a slider. In the beginning, we'll give it an initial angle, so that we don't need to be parallel to the wall. I give it an angle, so when the measuring axis is different from the vehicle's axis, it will prevent a miscalculation from happening. We added an adjustment for the servo in the program. This part over here, you can add this line into the program, and then test out your autonomous vehicle. You may find out about certain things. We will proceed with writing the next program according to this feature. We'll try and see the angle of the servo. We can use the control of the servo's angle to adjust the angle we want. This way we can correct the situation where we cannot determine whether the vehicle is getting closer or away when they are the same angle. Let's execute this program. The vehicle will maintain a distance of 10 cm and sway while moving forward. If I change the servo's angle to 90 degrees, it will bump into the wall. But for our vehicle, we want to do something that doesn't require the ultrasonic sensor to be facing forward. But we can predict when the vehicle is about to crash. This is what we'll do. We'll move the vehicle backwards. We turn the servo at an angle about 40 to 45 degrees, such as this case. We set it to 45 or 46 degrees. See that at this angle is measuring 14. Then here is 6 something. Here is 70 something. You can see that as it moves straight forward, and when it arrives at this place, the reading will drop. What does this mean? Here is 80 something. Then 90 something. And at 16, at its position, the vehicle can predict that it's about to hit a wall, because it will reflect back really fast. I can make this angle a bit smaller, about 30 something degrees. This angle will depend on the status of each vehicle. By experience, we would say between 30 and 60 degrees it works. This will depend on each one's program writing. We'll execute this using an angle of 30 to 40 something. If it is 40 something, its rating will be around 60 something. Let's execute this part next. Let's move on. Once you've finished practicing, we'll move on to the next topic. The next topic will be running in circles like this. In our explanation just now, you'll probably realize about our situation for reading when it's at 90 degrees. Since the angle of the ultrasonic sensor has changed, we'll measure a sudden drop in the reading. At this moment, the vehicle needs to make a turn. As for how much the vehicle should deviate and measure fixed distance, will change as the angle of the sensor changes. Let's take a look at our program. We didn't make any modifications. We only added a few adjustable sliders into the program. The first one is the fixed distance. Originally, it was set to 10 cm. We're going to adjust it. Why do we need to add this adjustment? Because later on, we will also adjust the angle of the servo. Initially, the servo's angle was perpendicular to the distance measured from the wall. When the ultrasonic sensor is beveled, D will also change. Therefore, after the servo's angle is adjusted, the distance must also be adjusted. It's more convenient to do so by using a slider for adjustment. At the same time, in order to adjust the vehicle speed, we also added a slider. There will be a total of 3 sliders. This PWM will be used to adjust the overall speed. Let's take a look at our program. You can try to run it. After that, we'll check the result of its execution. Okay, in order to facilitate control and adjustment, the servo's angle, the fixed distance, and the motor's PWM value will be placed in here for adjustment. We can adjust the optimal turning parameter. Let's see how they execute. What's the most important here is to see if it can turn 90 degrees smoothly. When this is done, you can practice this on your own. Once you're finished practicing, we'll do the final topic, which is to walk through a maze. This maze's walkthrough method is called the right-hand side rule, which moves along the right-hand side. In theory, as long as you can move along the right-hand side, you can move towards the end and exit the maze. You're only differing in how fast you do it. You'll probably think this is quite stupid, but this is the basic foundation. Right now, you might be able to move smoothly without hitting any wall. After that, we'll demand finding the shortest path. But there's more advanced class. Let's take a look at this program. What we need to pay attention to, as well as the logic, is the same. The only difference is that when we turn 90 degrees and 180 degrees, we must give it a directional change. We'll put our focus in that. You can take a look at this. This is the way I deal with this. When I turn 90 or 180 degrees, it's actually different. For example, when I turn 180 degrees, it's basically completely turned to the right. Since we're doing the right-hand side method, when turning 180 degrees on the right, I need to reduce the speed difference between the two wheels to avoid hitting the wall. If it is 90 degrees turn, I must accelerate. There are 2 ways to do so. One is that the moving axis needs to turn faster, while the other one is to make the other wheel to rotate in the opposite direction. You can give this a try. I have used a subroutines to single out the slider so that it looks cleaner, and it's easier to evaluate the program. You can try and run this program. You can also do this according to your own ideas. You don't have to follow this logic. The difference is in how you perform the speed difference for a 90 and 180 degrees turn. We'll later check the result of your own program. Let's take a look at this. We'll perform 180 degrees turn and 90 degrees turn respectively. We have set two types parameters. When turning 180 degrees, we need to slow down its speed during the turn. But when turning 90 degrees, we need to accelerate. The wheel that was originally stationary will remain so, but the wheel that was turning normally needs to speed up. Let's check the result of its execution. It has turned 180 degrees. The 90 degrees turn comes in pretty soon, so it needs to switch actions very fast. When you are practicing this, you can comprehend that the difference lies in the motion for 180 and 90 degrees. You can adjust the wheel speed difference or adjust the turning direction of the wheels, downward adjustment of the wheels. The way everyone does this is different, so you can show your own ideas. You can practice executing this. When our maze becomes more complex, it will depend on how much you understand the relationship between your vehicle and the parameters. In order to have a good calibration of the parameters, this class for use of ultrasonic sensor distance sensor for maze walkthrough is now finished. If you are interested, you can try the method to go through the shortest path, which is a very interesting challenge.